Hi everyone, I'm Mitra Peivandi. Today I'm going to present a lecture called Capacitors. I'm from the Pattern Recognition Lab and this is for the Electrical and Electronic Circuits lesson at Ferdowsi University of Mashhad. You can use this link to access the text of this lecture. In this lecture, we will explore the fundamental of capacitors. We'll begin by defining what a capacitor is and discussing whether it is a passive or active component. We'll then delve into various applications of capacitors, followed by the derivation of capacitance in a flat capacitor. Finally, we'll examine capacitor behavior in circuits, including charge curves, characteristic time, resistor voltage during charging, the functionality of RC circuits, and the concept of a capacitor as a storage battery. First of all, I want to talk about the fundamentals for all capacitors. First, what is a capacitor? Capacitor is a device for storing electrical energy consisting of two conductors in close proximity and insulated from each other. In this picture, you can see the different type of capacitors. First of all, we have polar capacitors. Next, we have non-polar capacitors. And the third one is variable capacitors like trimmer capacitors. Next, let's consider a parallel plate capacitor like this picture below. It's a very simple schematic picture of a parallel plate capacitors. These plates called conductor electrodes, the area between them is the dielectric and this line is wires. Let's find out more about capacitors. Are they passive or active elements? Passive element is a element that do not provide power gain. They can store or dissipate energy, but cannot generate it. In opposite, active element can provide power gain and can generate energy. And as you see in this picture, there are some active elements and passive elements. And capacitor is right here in passive element. So capacitor do not provide power gain and it can just store or dissipate energy. Next, let's talk about its applications. First of all, energy storing is the main role of capacitor. Next, we have bypass capacitors that also called decoupling capacitor, which is used to filter out unwanted noises. And next, we have the application which is reducing radio interface. Arcing contacts can create unwanted electrical noise and interference, which can disrupt radio signals. But capacitors and resistors can work together to reduce this interference. The role of capacitor is that they can help to filter out high frequency noise generated by arcing contacts and smoothing the electrical signal. The role of resistors is that they limit the current flow and help dissipate the energy from the noise. Next, let's talk about the capacitance and find a formula for that. The capacitance is equal to Q divided by V, which is the voltage across plates, and Q is the charge stored. And for parallel plate capacitors, we have this equivalence, which is electric field is equal to voltage divided by D, which is the separation between the plates. By applying the Gauss law, we can obtain this formula, which is for electric field. Electric field is equal to sigma, which is the surface charge density, divided to epsilon, which is the permittivity of free space. And also sigma is the surface charge density, so it is very clear that sigma is equal to charge divided by A, which is the area. But by doing some mathematics, we can obtain this formula, which is the capacitance is equal to kappa, which is the relative permittivity of the dielectric material, or also called the capacitance constant, times epsilon, which is the permittivity of free space, times A, which is the area of the plate, divided by D, which is the distance between two electrodes. To get an idea of what a farad is, let's calculate area which would be necessary in a capacitor to have 1 farad capacity. A is equal to C times D divided by kappa times epsilon. If kappa is equal to 1, D is equal to 1 millimeter, and C is equal to 1 farad, A is equal to 113 million square meters. In application, it's not even possible to build this capacitor with this much area. So a tendency toward higher values of kappa is now clear for you. In this table, you can see the dielectric constant for common insulators at 25 degrees centigrade. Now let's find out the capacitor behavior in a circuit. In this circuit, we have a battery, switch, resistor, and capacitors. A charging curve is obtained from this formula, which, as you see, it has exponentially relation. In this plot, we have the voltage across capacitors in RC circuit for different R and C values. As you see, they started from a single point, but they ended charging in different times. We can define a parameter called tau, which is equal to R times C. That 5 times tau is kinda equal to the time is needed to charge a capacitor. So in the orange one, for example, 5 times R times C is equal to 40 seconds. And as you see, after 40 seconds, the voltage is very close to 4 volts. It's good to know that in charging capacitors, after being fully charged, the voltage of them is completely equal to the voltage of the voltage source. So in this case, that our voltage in voltage source is 4 volts, it's very clear that it should get to the maximum value of 4 volts. But for example, in this blue line, 5 times 1 times 2, it's 10 seconds, and you can see after 10 seconds, it reached the value of 4 volts. Let's find out the resistor voltage during capacitors charging. By doing some simple mathematics, we can obtain this formula. In this plot, you can see the voltage across resistor versus time during capacitor charging. And now, let's find out how does an RC circuit really work. First of all, when the switch is first closed, the entire voltage of the battery appears across the resistor and not across the capacitor. This is because initially the capacitor acts like a short circuit for an instant. And voltage change over time. As time progresses, the voltage across the resistor decreases while the voltage across the capacitor increases. This change follows an exponential curve as the capacitor charges. This is the exponential curve that we discussed. And after that the capacitor in our RC circuit is fully charged, the behavior of the circuit changes significantly. And so capacitor voltage is stabilized and current drops to 0, so voltage across the resistor is 0 too. In real world application, what happens next actually depends on the circuit design. If the circuit is left as is, it will remain in a steady state. While if there is a discharge path, this path will allow the capacitors to discharge. For example, this is a circuit that the discharge path is occur when switch 2 is closed. First of all, consider that switch 1 is closed. Now, capacitors is start charging until it reach the voltage equals to the battery voltage. In this time, the I is equal to 0. But if we open the switch 1 and close switch 2, there is a discharge path for capacitor and the current flow through the resistor.